Hello and welcome to Friday's edition of Cracking the Cryptic, where today we have a puzzle with a magic square in it. Now I haven't done one of these for ages, so I'm looking forward to this. I think it's a debut on the channel as well. This is for Chris C, who apparently goes under the Discord handle of It's Chris Official, so you may want to look out for Chris there. It's called Twisted Magic, and I think the grey cells are going to be the magic squares in this one. And this has been recommended to us by a few people, but amongst those are full deck and missing a few cards. So well done for finding a puzzle that apparently pleases our testers mightily. Now, do I have anything to tell you about today? I have a couple of things to mention. We're going to be streaming tonight, I hope. I did download a game called The Last Cube yesterday. It did work on my computer, so I'm hoping I will be able to stream it. We plan to start about 10 PM UK time. We'd love to have your company, and you can admire how useless we are at a game that, well, I think you have to move around a landscape and solve puzzles. It's a bit like The Witness, except you have to control a cube. It sounds fascinating. I've been watching the reviews of it on Steam since it came out yesterday, and they all seem to be quite positive. So hopefully this will be a good experience for us. Hopefully it will be amusing for you guys to watch. And as I say, 10 PM tonight if you want a laugh. And the other thing I need to mention today is I need to say a very, very happy birthday to Jeffrey. Your partner Ethan got in touch with us, Jeffrey, and said that it was your birthday today, and you both enjoy the channel mightily, so which we were delighted to hear. So I hope you have a super day. I know you're off on a trip soon. I hope that goes really well, and I hope you have a great cake today. Anyway, let's get on with the rules of Twisted Magic. They are as follows. Normal Sudoku rules apply. In cages, digits must sum to the small clue in the top left corner of the cage, and digits cannot repeat within a cage. So that's telling us that those three cells there sum to 14, and what we cannot do is try something like that. Because although these sixes don't see each other in the normal Sudoku way, they do share a cage, and that's not allowed. So don't do that, you'll get the puzzle wrong. Clues outside the grid give the sum of the digits along the indicated diagonal, and digits may repeat along such diagonals if allowed by other rules. So that's telling us that those three cells there, in fact none of these, that last bit of the rules is irrelevant in this puzzle, because you could never have a repeated digit along that diagonal, because it would only add up to 18. Because if you did repeat a digit, they would definitely be in the same box of the Sudoku. If you tried that, for example, that's not going to work. Those three add up to 19, and those three add up to 14. Now, what else? Here's the magic square bit. Digits in shaded cells must form a twisted magic square. So that's these cells here, with no repeating digits. A magic square is where the row, column, and main diagonals, ignoring the unshaded cells, all sum up to the same number. So let's have a think about that. So what we're learning is, well, we're learning firstly these are the digits 1 to 9, because we can't repeat a digit in the grey cells, it says. And then those three cells, whatever they add up to, and now if you know the secret, you might be able to work out what they add up to. But those three cells add up to the same as those three cells, add up to the same as those three cells, and then the diagonals will be those three cells, and those three cells also have to add up to our magic number. So do have a go. The way to play is to click the link under the video as usual, but now I get to play. Let's get cracking. I'm going to start with a magic square. It is ages since I've done one of these on the channel, but we can say all sorts of things about these digits. You may be interested to know you can immediately write a 5 in there, and that is because of the secret. Let me explain. So if we know that these digits are all different, and we do, then because of the secret we know what all of those grey cells add up to, because the secret is that any complete row, any complete column, or indeed any complete box of a Sudoku contains the digits 1 to 9 once each, and if you add up the digits 1 to 9 you get 45. So if those grey digits add up to 45, and they do, then what does each row of this magic square need to add up to, given they all add up to the same number? Well, we can express this. If we say that row is x, then that would be x, and that would be x. So 3x equals 45, therefore x equals 15. But you may be saying, well, how do you know that's a 5 then? Well, that's a little bit more mathematics for you, because let me, and the only reason I know this is because I've done it, but I've seen it before and explained it before. So let me explain how we know this is a 5. Now we know that everything adds up to 15. So if we know that every row, column and diagonal in the magic square adds up to 15, then I want to highlight those squares. That's one of the diagonals. I'm going to highlight that in yellow, so we know that adds up to 15. I know that that adds up to 15 as well. The greens add up to 15. And now I'm going to do this column. I'll make that purple. We know the purples add up to 15. And I'm going to do that row. That adds up to 15. So all of the colours there, each individual set of colours added up to 15. And there are 4 different colours, you can see, because the central cell there is actually highlighted 4 times. So that means that we've got 4 lots of 15, which 4 times 15 is 60 in those cells, if I count this one 4 times. Now, but we know individually that those 9 cells, if I just take the 9 cells but I don't count this 4 times, I just count it once, these 9 cells add up to 45 because of the secret. So if I was to remove each of these digits, each of these coloured digits from our equation, if you like, and I'll remove one colour from this cell because I want to remove one lot of 45, so I'm going to uncolour all these. This would retain, actually that was a bit unclear how I did that. So all of these become uncoloured, and this one loses one of its colour because I want to remove one of the digits. Then we know that 3 lots of this digit equal the difference between 60 and 45, which is 15. So if 3 lots of this digit equal 15, what's this digit got to be? Yep, you know it. It's a 5. And that is how I know this is a 5. But we can go even further than this with magic squares. For example, we could say that this square, well, this square has to be even. The 4 corners of a magic square involving the numbers 1 to 9 are always even digits. And the way to prove that to yourself is to think about what would happen if this was an odd digit. In particular, what would happen if this was a 9? Now, if it's a 9, that would imply that there must be 3 different ways of making 15 using a 9 in a magic square, because that would be one way. Let's just put 9 in here. That would be one way. This would be a second way. And this diagonal would be a third way. Now that's never going to work, because although you could put 1 in here and that's going to work, these two have to add up to 6 without using 5 and 1. We can do that as well. That could be a 2 and a 4. But now we have a big problem with making this domino add up to, well, not domino, these 2 cells add up to 6, because there are no options left. We can't do double 3. That won't work because, well, we'll definitely be repeating a digit in the magic square as well as the 15 cage. So you can't make this work. It won't happen. And that tells you, because the logic's symmetrical, of course, that means you can't put a 9 in this corner. It means you can't put a 9 in this corner, or this corner of the magic square. So now we have, well, I've lost my 5. Sorry about that. But if you can't put a 9 in any of those cells, you must put a 9 in one of these cells. What's going to go opposite 9 on the magic square? Well, 9 plus 5 is 14. We know each row, column and diagonal adds up to 15, so the 9s and the 1s must be opposite each other. And now you can think about where 7 can go in the magic square, for example. So if we try and put 7 here, can we make that 3 different ways? And you'll find that it won't work. You'll end up with exactly the same pattern for 3s and 7s as you had for 1s and 9s. So you end up having to put all the odd digits in the sort of intermediate cells, and all the even digits are sort of left over in the corners. And that presumably is what we're meant to know before we start Chris C's puzzle. Now, let me just have a stare at this for a moment or two. Oh, I tell you the other thing we've got. So as well as being given the sort of magic square properties, which hopefully many of you knew already, what about this 10 cage and that 10 cage there? There's only one way of making a 10 cage in 4 cells. Those have got to be 1s, 2s, 3s and 4s. Now I'm noticing things. That's a 1, 2, 3, 4 quadruple in row 8. Yeah, okay. There's all sorts of colouring opportunities going on here. Because there are two things I'm now seeing as a result of that. The first relates to row 8. So that means these cells, the remaining cells, have to be 5, 6, 7, 8 and 9. And I'm wondering whether what we've got to do here is sort of colour low digits and then colour digits that are 5 or higher in a different colour. Let me just think about that. That can't be 5, obviously. So that's a low digit. Yeah, that's interesting. Yes, let's keep going with this. I'm actually going to colour low digits in one colour. I will use blue for icy, nearer to 0, and I will use orange for sunny for those digits. Okay, so the reason I think this is interesting is look at this 10 cage in row 9. Let's think about the nature of a domino 10 cage. It must have a low digit in it, i.e. a digit that's a 1, 2, 3 or a 4, and it must have a high digit in it, a 6, 7, 8 or 9, not 6 in this case. But it must be of that orientation. And that means in row 9, the digits 1, 2, 3 and 4 have to occupy 4 of those 5 cells. And that means the rest of this row must be sunny. And that means, well, those two are, oh yeah, look, in this box we can just sunify those digits as well, which means this must be an icy digit, so that's a 1, 2, 3 or 4. Same thing here, we'll sunify those. So we've now got 4 sunny digits in row 7. Oh, okay. So if that's a sunny digit, that is an icy digit, isn't it? Because that's another 10 cage over here. We've got a 14 diagonal. I haven't really thought about the diagonals at all yet. That one's quite large. The way to get a handle on these so-called little killer clues quickly is just to divide the total by the number of cells on the diagonal and see how close to 5 you get. The idea being you hope you get nowhere near 5. Here we get to a number that's just over 6. So we know this diagonal has a slightly high average. That one we know it's exactly 6. Again, a slightly high average. This one is a very slightly low average, but that's not very useful. Even knowing that these two digits are slightly low, and this is a high digit, I'm not sure what exactly we can. Well, this can't be a 5, can it? Because we can't make those add up to 9, and it can't be a 6. The maximum we can make those is 7. So the minimum we can make this is 7. So this is 7, 8 or 9, and that's 1, 2 or 3. Oh, it's not, actually it's not 2. Aha! So this is down to being quite specific. Now, the other thing I'm seeing here is box 5 now has an absolute plethora of odd digits in it. And that's very interesting. Well, actually, no, it is very interesting. It's very interesting for 2 reasons. Firstly, the gaps in row 5, because we've got all the odd numbers catered for in this little X pattern, these must be all the even numbers. Now, what I've noticed now is that in this column and this row, I've now got all the even digits placed. So that digit cannot be even. And this digit has to be 1, 3, oh, that has to be 1, 3, 7 or 9, but it's not 1 or 3 because there's definitely a 1 and a 3 in that quadruple in the bottom row. So that's just 7 or 9. That's not 5. So we've now got a 7-9 pair in box 8. So that's not 7 or 9. That's not 7 or 9. That means that's not 1 or 3. So now we're down to even numbers in the 10 cage. And in this column we haven't placed 1 and 3, which must live at the top of the grid. So that's got to be a 7 or a 9 in this 10 domino. Okay. So can we go further than that? That can't be a 4 because this would be a 6. So that digit is 7, 8 or 9. Don't know. I'm not sure. There's probably some stuff we can do, but I don't know what it is. I suppose this row as well, look, we've got all the even digits in this row. I can tell you that domino adds up to 10 by virtue of the secret. Because if you think about the nature of what we've already placed in row 5, those digits there add up to 25. We know the whole row adds up to 45, and that domino adds up to 10. So that adds up to 10 as well. And these have all got to be odd digits that aren't 5, haven't they? So this is either 1, 9 or 3, 7. And the corollary of that is that this is either 1, 9 or 3, 7. Yeah. Yes, actually, look at this 10 cage here. It's not got a 2 in it. So what would happen if it didn't have a 1 in it? Well, then its minimum constituents would be 3, 4 and 5, and 3, 4 and 5 add up to 12, so there is a 1 in here, and it's not on the 19 diagonal, because if it was, you'd have to put double 9 on the 19 diagonal, and that's an idea so ridiculous that I cannot tell you or abide it. So we must put 1 in one of those two cells. The other two cells add up to 9 now, and they're not 1, 8 or 2, 7, so we've either got 1, 3, 6 or 1, 4, 5. Which I could pencil mark that, I suppose. 1, 3, 6 or 1, 4, 5, with the 1 not being here. So this digit is a maximum of 6, which means these two digits are a minimum of 13. I don't know, that's a little bit restricted, but it doesn't seem to be restricted enough. We know the parity of that digit, look, because we've got a 14 total for the cage, and this is even and this is odd. So that means this has to be odd, and it's not 1 or 3, so that is 5, 7 or 9. Which is almost very interesting for this column, look. We've now got 4 odd cells and 3 even cells. So we know that these two cells, one of them's odd, one of them's even. I'm not sure whether this is meant to be a high-low puzzle or an odd-even puzzle. It could still be either, I think. But I might have done the wrong colouring at the bottom. This colouring might be otiose very soon. We might be meant to go to parity colouring. Right. Oh, I see. Right, each of the cages going around the twisted magic square has a parity implication. Yes. Look, this is an odd cage. That's an odd number. So these two must add up to an even number, and that's even. So that's even as well. So that's 2, 4, 6 or 8. This one needs an odd number here in order for the parity to work. So that's 1, 3, 5, 7 or 9. Those are not 7 or 9 because of the 7, 9 here. And this one's a bit lower, isn't it? So again, we can do parity though. This has to be even, 2, 4, 6 or 8. And is that interesting or not? I'm sure it is somehow. So what have we actually learned from this? We've learned these two digits had a little bit of a restriction from the absence of 1, 3 from this one and the absence of 7, 9 from this one. But does that actually help us? That's the question. Wondering if there's something going on with the magic square here, because obviously those two digits add up to 10, because we know that this diagonal of the magic square adds up to 15. So these two add up to 10, so that's either 2, 8 or 4, 6. But these cages add up to 30, so these two dominoes add up to 20. Does that mean... I was wondering if that meant one of them has to have a 9 in it, but I'm not sure that's true. No, I don't think that is actually true. 7, 7 would be 14, 5 and 1 would work. Okay, so I've got to think harder. That's what we've learnt. Bobbins. Oh, actually, you know what? I do have to be careful here. I looked at this digit a minute ago and I thought, ah, that's really clever. Good grief. I thought, could it be 1? And I concluded yes. And the reason I concluded yes is I looked at those two digits and said, could they add up to 15? And they can. But of course they can't because of the magic square. Because if this was a 1, if these two added up to 15, that would have to be a 0 to make the magic square work, which it can't be. So that's a 3 or a 5. So actually, so now this can only have 2 options, surely. Because if this is 3, these two squares add up to 13, and we know this square's a 2. If that's a 5, these must add up to 11 from its cage perspective, but those add up to 15, so that's a 4. So this is now only 2 or 4. And that might be very useful then. So presumably I've got to play this game all the way round here. So I think I've got to think about these hinges of the cages and the implications for the sort of next digit along. So let me just think about this. So if that's if that's now a 2, that would have to be a 4. So we'd have to go 2, 4, and that would have to be 9. And that would have to be 2. Oh, no. Much easier. That's a 2 or a 4. Its opposite number on its magic square, these 3 cells add up to 15. So this has got to be a 6 or an 8. So now, now can we do better? Do we know something useful about the world now? That's the question I'm asking myself. Yeah, this is very strange. It really is. Because now with this only being 8 or 6, the options for this digit have sort of narrowed substantially, haven't they? Because this clearly can't be 8 now, because that's going to make this cage have more than 13 in it. Similarly, it can't be 6. So this comes down to 2 or 4, which means these two cells in the 13 cage are either adding up to 11 or 9, but those 3 squares add up to 15 always. So this square is a 4 or a 6. So it's no longer able to be 2 or 8, which means that square opposite on the magic square is now 4 or 6. And now, yes, so now I've got a 4, 6 pair on my magic square, haven't I? I must have. If I've got this down to 4 or 6, and that diagonal adds up to 15, that's 4 or 6. So we can take 4 and 6 out of those 2 squares, and they become an 8 and a 2. And now this domino has to add up to 5, so we can remove 7 and 9 from that one. So this is down to 1 or 3. 4 and 3 is 7. That could be 9, couldn't it? Or 6 and 5. Yes, okay, and then this one has the opposite sort of situation. If this domino is maxed out, it would be 6 plus 5. So this square needs to be at least 5, so it can never be 1 or 3. These have to add up to 13, so that can never be 1 or 3. That's a 7-9 pair, so that means that's not 7 or 9. This is a 1-3 pair, doesn't resolve my 10 cage. But that does. That's a 4 or a 6, so that can't be a 4, 6, 10 cage. That's beautiful. So that's 8, and that's 2. So that's not 2, which means that's not 8. That's no longer 8. This is no longer 2 or 8. Ah, this is spectacular. Look, 1, 3 there. Where do they live in this box? Well, the 1 can only live in this cell here. So that's 1, that's 9. That's 3, because it's the only place the 3 can live. These add up to, these add up to 13, and either option is available. But we must be close to cracking. The thing is, once we get the magic square cracked, we can fill in loads of digits around the middle. These add up to, yeah, there's still 2 ways of doing this, I think. I think we could go 4, 9, or 6, 7. So this square, by Sudoku, is 4, 5, or 6. Oh, bother. I'm sure this is resolved somehow. I just can't see how to do it. This is making me feel very stupid. I've got a 1-3 pair in this row. Oh, look, I've got a 1-2 pair in blue. So those are not 1s and 2s. So these are 1s and 2s. So these are not 1s and 2s. So these are 1s and 2s. Whoopsie. Misclicking all over the place. Aha, that's beautiful. Right, now this diagonal is fixed. Well, maybe not fixed, but there's no way I can put 7 in here anymore, because I can't make those add up to 7 anymore. They need to be 3 and 4, and the 3 and 4 are down there. So this is 9. That's 1. Oh, well, I can see what that's going to do. Oh, I can't resolve those yet, I don't think. But this 1 is very powerful. Remember this domino added up to 10. Well, it's not 1, 9 anymore. So that's 3, 7. This is 1, 9. But more interesting than that is that this has now become a 3 on our magic square. So now we can fill in everything. We just got to make sure everything adds up to 15. And now it does. There you go. We've finished our twisted magic square. This is very beautiful indeed. Now that's not 4. So those are not... Right, those are not 4, 6. These are not 2, 8, therefore. And I'm sure we can probably resolve this somehow. Oh yeah, look. Now we can do the hinges because we know the contents of the cages. 9 there, so that's got to be 6. 7 here, so that's a 7. That's a 9, therefore. So this is a 1 and this is a 3. This hinge here needs to be a 2. And that's it. We've sort of done the cages around the middle box. This 2 fixes the 2 and the 1. Oh, yes, 1 had to live in that 10 cage, and it's not there anymore. So actually, this is the 1. So this is either 3, 6 or 4, 5. I don't know if we can do that. Well, that's not 3, actually. Well, not 3. So that's not 6. This column needs 4. Well, that's got to be a 4 or a 5. That doesn't fix this at all. Okay. So where should we look now? I sort of feel like we're on the right path here. We haven't finished it yet. Oh, 1 I can place in this column. You can see we've got a 1, 2 pair here and a 1, 9 pair here. So where does the 1 go in this column? It can't go in those 6 cells, it can't go here, and it can't go there. So that's become a 1, which might be helpful. Oh, this being a 2 means we can finish our 14 diagonal, so we get a 3 and a 4 at the bottom of the grid. 4 must be in one of those cells, so 4 must be in one of these 3 cells. And 6 by Sudoku is exactly there. So these digits are now known. Look, they are 4, 5 and 9 to complete box 4. That's not 9. And these squares are 2, 3 and 8. Oh, that's quite handy because we've got a 2 here. Yes, so what we could have done is just filled in the 2s and the 8s in the middle box. I just didn't spot it, apologies. So those squares are now 4, 7 and 5. Which doesn't seem to be resolved by anything. 6. So 6 is in one of 2 places at the top of the grid. Column 1. That can't be 4, 5 now, because that was going to break this square, which has to be a 4 or a 5. So this is 3, 6. So that's a 3, that's a 6, that's a 6. Is that right? So have we really got, yes, we seem to have 4 6s looking at this box, so that's got to be a 6 and a 4, which means that's not a 4 anymore. This domino here is either 2, 8 or 3, 7, and it's not 3, 7, there's a 3, 7 in the row. So this is 2, 8, which doesn't seem to be resolved, but that does resolve this 3, 8 pair. And it does resolve the 1, 2 at the bottom there, and that resolves the 1, 9. So now in this column, look, we've not placed, I think we've got to have 5 or 7 into this cell at this cell here, which doesn't seem to be resolved, but I feel like we're on the right track anyway. Okay, can we really put 2 in there and make this 18 work? It would have to be 7 and 9. No, you can't do that, because if that was 2, 7, 9, where are you going to put 3 in this box? The answer is nowhere. Yeah, so one way of seeing this is that 3, in fact, now has to be on that diagonal. So this has to be an 8. That has to be a 2, and now those 2 squares have to be 3 and 7 to make 18. These 2 squares are 9 and something, 9 and 5. We can place the 9, place the 5. That's not 5 anymore. What do we need in this row? We need 4s and 2s. Yes, we can do that. That's 2, that's 4. Oh, I've got 3 on this 19. Yeah, that's fine. 3 on the 19 diagonal, so those 2 squares add up to 16, and there's a 9 there, so that's got to be 9, 7. That's got to be 3, 7 now. So that's no longer 7. This digit has got to be 5. Just by Sudoku, we need 3, 4, 5 in the column, and there's a 3, 4 pair here. So that's 5, that's 4, that's 4, that's 3, that's 7, that's 5, that's 7, that's 8. And we might be about to get somewhere good here, I think. 7 comes out of there. 3 fixes the 3s and the 7s on this side of the grid. What do we need in those squares? We need 5 and 8. Must be done, is done. 8 and 5. That gives me a 4, 4, 6, 5, 6 here. These 2 squares have got to include an 8 and a 5. So that's all working nicely. That's no longer, that is just 9 by Sudoku. That's a 4, that's a 5. And this row needs 6 and 7, which we can fill in. Finish that. Finish this. Plonk an 8 in the corner, doesn't get a song, looks correct. Yay. Fabulous. Absolutely fabulous. Chris C. Take a Bow. That was a lovely, lovely twist on a magic square puzzle. I haven't done one for years. But yeah, it was nice to remember the logic, and it was a very, very clever. I don't quite know whether I did this correctly either. I I started off with low-high colouring, and there might have been a more efficient way of doing it, but I really liked the way that these hinge digits actually really affected how the magic square worked once I got my head around it. I did enjoy that mightily. I hope you did too. Let me know in the comments. I do enjoy them, especially when they're kind. And we'll be back later with another edition of Cracking the Cryptic and a live stream as well. Hope to see you then. Bye for now.